The idea that underlies everything is called the fundamental counting principle. And here it is. If you want to count all the possibilities for something, you have to ask two questions. How many independent choices do you need to make in order to create a possibility? And then how many options are there for each choice? So this will make more sense with an example. True story. Once upon a time, I only owned 3 pairs of pants in my entire wardrobe. I forget how many shirts I had, but let's assume I had 10 shirts, and let's assume I had a hat. So I might ask, like, how many total outfits are possible for me? So if I'm going to put together an outfit, I need to make some choices. I need first to choose a pair of pants, and then I need to choose a shirt, and then I need to choose whether or not to wear a hat. So I make 3 choices. So here's pants, shirt, hat. So I said I have 3 options for which pair of pants I'm going to wear. I have 10 choices of shirts, and I have 2 choices of hat, not because I have 2 hats, but one choice is to wear a hat, and the second choice is don't wear a hat. So the fundamental counting principle says that you multiply the number of options for each choice to get the total number of possibilities. So here this would be 30 times 2 is 60 possible outfits. This sort of makes sense if you think about it. Let's say my pants are like jeans and khaki and dark jeans. And my shirts are brown and green and red and yellow and orange and purple and etc. So you can like list out all the possibilities. I could choose, and let's pretend I don't have a hat anymore, okay? So I could choose jeans with a blue shirt, or jeans with a green shirt, or jeans with a red shirt. Or I could choose khakis with a blue shirt, and khakis with a green shirt, or khakis with a, red shirt. So it's like for each one of these, I could choose any one of those. So for each of these 3 things, I have 10 choices over here, which is the same thing as 3 times 10. So that's the kind of intuitive reasoning behind why the fundamental counting principle works. Okay, so let's do another example. Let's use permutations as our example. So I've got 10 books. I want to know how many orderings. How many ways could I put those 10 books in a line? So if we want to break this down into choices, I could ask, how many options do I have for the first book? And then how many options do I have for the book I'll place next to it? And how many options do I have for the book I'll place next to that? So I've got 10 options for what could be my first book, but then after I've chosen my book, I only have 9 options for what the next book could be, because I've already chosen one. And then once I've chosen the first 2, I have 8 possible choices for the third book, and so on. By the time I've chosen 9 books, I only have 2 options for that 9th book, because I've already placed all the others. And then once I've placed the 9th book, I don't have any choices at all. I only have 1 possibility for what the 10th book could be. So the fundamental counting principle says I multiply the number of options for each choice, and so that gives me 10 factorial, because it's 10 times 9 times 8. And you can see that in general, if I had n books, and I wanted to put all n books in order, I'm making n choices. What's the first book? What's the second book? What's the third book? All the way down to what's the nth book. And it's going to work out to be the same, n factorial. Okay, well that's not exactly the same as my permutation equation from before, right? Because before I wasn't putting all n books in order, I was choosing r books to put in order. But you see it's going to come out just the same. If I have n books and I want to choose r of them, what that means is I'm making r choices. So there's going to be r of these. There's n ways to choose my first thing. There's n minus 1 ways to choose my next thing, because I've already chosen one of the available ones. N minus 2, and so on. And then down here, it's going to be n minus r minus 1. And so this is a falling factorial, as we discussed in our last video, that's got n total terms. In the actual equation, we ended up writing it this way: n factorial divided by n minus r factorial. And it might not be obvious why is this thing the same as that thing, but it will be with an example. So let's say I have 10 books and I'm choosing 4 books to put in order. 10 choices for the first book, 9 choices for the second book, and so on. I hope that it's clear that this is the same thing as 10 factorial divided by 6 factorial. Here's why. 10 factorial, if I'm going to expand it out, looks like that, all the way down to 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So if you think about what's canceling here, the 6 factorial is canceling starting at 6 all the way down to the ground, all the way down to 1. And so the only thing that's left over is this 10 times 9 times 8 times 7. So it's sort of like imagine that you start with 10 factorial, but then divide by whatever factorial starts with the number after the one that you want to stop at. And so in general, if you're stopping at r minus 1, then you need to start dividing by the factorial at n minus r, which is this next one. So that's the derivation of the permutation formula. But I think it's confusing to think about it in terms of this formula. I never think about it in terms of this formula. I always think about fundamental counting principle. I just think how many choices for the first, how many choices for the second, and then you don't have to mess around with, factorials divided by other factorials. You can just think about it in a more natural way.